There should be 3 distinct layers in the shop. Pour Kahlua into it. Pour Kahlua into it.
The second part of the rates, equilibrium and pH module concerns the equilibrium constant. Dynamic equilibrium is established when the rate of forward reaction is equal to the rate of the reverse reaction, and the concentrations of reactants and products remain the same. A bulk of this section concerns the equilibrium law. The equilibrium law tells us the relative proportions of reactants and products present at equilibrium. For this equation, Kc equals products over reactants, so we can write the equilibrium law as Kc equals C to the power of little c, because the concentration of C to the power of little c, I should say, the concentrations are raised to the stoichiometric numbers, times by d to the power of little d. Products always go on top, and a similar thing on the bottom with capital A to the little a, concentration of the stoichiometric number, times by b to the little b. As an example, this is the formation of 2 NO2 molecules from nitrous oxide. The rate equation for this is Kc equals, not rate equation, equilibrium law, is NO2, concentration of NO2 to the power of 2, because that's what the stoichiometric number says, right here, over the concentration of nitrous oxide. Similarly to how we can work out the units of the rate constant, we can work out the units of the equilibrium constant by cancelling out moles per decimeter cubed. So in this instance, we'll cancel 1 from the top, because it's squared, and the 1 on the bottom. We'll get that the units of Kc are moles per decimeter cubed. The value of Kc gives us an insight into the position of the equilibrium. If the equilibrium favours the forward reaction, the concentration of products will be greater than the concentration of reactants, which means that the value of Kc will be above 1, because the numerator is bigger than the denominator. On the other hand, if the equilibrium favours the backward reaction, there will be more reactants than products, so the value of Kc will be less than 1. Hence we can say that if Kc is above 1, the equilibrium is shifted to the right, or if it's less than 1, it's shifted to the left. You also might have to consider the effective temperature on the equilibrium constant. This depends on whether the reaction is exothermic or endothermic. So for an increase in temperature in an exothermic reaction, the equilibrium will favour the products, as that is the endothermic reaction, and vice versa for decrease in the temperature. It's important to note that Kc is only affected by temperature, and it's unaffected by concentration and pressure. The reason for this being is, for example, if the concentration of products doubles, the initial value of Kc halves, so the system shifts to the left to increase the Kc value back to the original. And finally, the presence of a catalyst also does not affect temperature because it speeds up both forwards and backwards reactions.